of what it tells us about nature, this is close to the last word, is not as beautiful as it should be. It's based in particular on the idea that there are four fundamental forces: gravity and electromagnetism, which are classic forces of nature, and two that were discovered relatively recently, the strong and weak forces. So 4 forces is 3 too many. We'd really like to have a unified description that was coherent, where everything was described in the same language and fit together. Similarly, there are different kinds of matter. There are quarks and gluons and photons and electrons, and these come in various varieties. We'd like to have just one kind of matter and see the different manifestations of that stuff as fundamentally the same. So we're not satisfied. What makes me optimistic is that we have, in fact, beautiful ideas that I'll discuss with you about how to do that kind of unification, how to make our pictures of nature much prettier. And we even have some little hints, some circumstantial evidence, some encouragement from nature that these ideas are on the right track. But we haven't had the tools to really confront the ideas with experiment to see if nature agrees with our taste and allows us to consummate this unification that seems so tantalizing. The reason I anticipate a new golden age coming very soon is that at last we're going to have the tool that will enable us to tell if that's on the right track. I also anticipate that it is on the right track, and that will open up the first golden age of physics in the 21st century. So let me describe the tool. It's called the Large Hadron Collider, or LHC. This is a crappy pointer. If you fly to Geneva on a clear day and look down, you may see this kind of mystic scene with mist off there in the background, Lake Geneva, the city of Geneva, the Alps, and then you notice this very strange red circle on the ground. That's the LHC. It's our civilization's answer to the pyramids. 18 miles or 27 kilometers around. Of course, I'm joking. You don't really see the red circle on the ground. The whole thing is 100 meters underground, basically. And what it is a gigantic ring. And what's happening in this ring is that protons are being accelerated until their velocity is within 1 part in a trillion of the velocity of light, the limiting velocity. So they have enormous energy. There are 2 beams circulating around the ring in opposite directions, this away and that away. And at a few points, the beams are made to cross so that collisions occur. In these collisions, we reproduce in a very small volume and for a very short time conditions last seen in the natural world when the universe was about 1/10 of a second, 1/10,000th of a second old, getting very close to the Big Bang. We call these little bangs. So enormous concentrations of energy are in a very small space there in these little bangs, and we're probing extreme conditions of nature that we haven't been able to access before. To guide these protons around, you have to use very powerful magnets, things moving that fast don't want to be deflected from their straight line course. They have a lot of inertia. So this is what's actually inside the tunnel underground. 18 miles of these superconducting magnets. So these are like the magnets you would be inserted into if you're getting an MRI at a hospital, but a little stronger, well, considerably stronger. They have to be aligned with micron precision because the protons have to match up and make a nice circle going all the way around. Because it requires enormous currents to generate the electric fields, the magnetic fields that these magnets have, and the currents would dissipate enormous amounts of energy unless they were superconducting currents. The whole thing has to be superconducting, so you see this plumbing out here, which brings all these magnets to 2 degrees above absolute zero, where they're held. This is the coldest place in the universe on a large scale. Even interstellar space is filled with the microwave background radiation, which is 3 degrees. Making all these things work is a hard job. Every single magnet has to work correctly. There can't be any leaks. So the people who work on these things are very dedicated. They work very hard. You can see they get pretty tired. This is what the detectors look like. Give you an impression. Here's the humans on this scale. It's the size basically of an aircraft hangar. But unlike an aircraft hangar, which is empty, this thing is filled with extremely accurate, state-of-the-art, fast electronics and sophisticated signal processing equipment so that you can monitor what comes out of these collisions, which is a bunch of particles of different kinds, so this debris, moving at very close to the speed of light, but you want to know exactly how fast they're moving, so you have to measure their positions and times extremely accurately as they come out. You want to know what kinds of particles they are, so you bend them in magnetic fields, you send them through matter. We've developed very sophisticated ways of telling one particle from another. You have to realize they don't come with labels. So to really do justice to what happened and try to reconstruct it, you need a lot of information, and that's why these detectors look the way they do. And they're marvels of engineering and scientific know-how. The output can be thought of as pictures like this, which tell you what comes out of a collision. But this picture doesn't nearly do justice. It looks complicated, but this doesn't nearly do justice to how complicated it really is. First of all, this is a two-dimensional projection. You have to think that these are actually moving out in different directions. You have not only, but this is also a static snapshot. Each of these has to be tracked in time so that you know how fast they're moving. These things that look like noise in the background or how much energy is being deposited, and you have to keep track of that and which goes with which particle and so forth. It's a tremendous job to try to keep track of all that. And you have to look at something like 1 billion such collisions per second. That's how many are produced in the, and we're looking. So it's a big job. The flow of information is petabytes per year. To translate that into something more accessible to intuition, that's equal to the information of having 500,000 telephone conversations recorded with absolute fidelity all the time. But these events have much more content than the telephone conversations, and we want to do justice to the information. And so, to do that, new computer architectures have been developed. This is called the GRID project. What you see here is about 1/1000th of the grid. There are about 100 sites like this. This is the one at CERN, and this is you're seeing about 1/10 of that site. It's a lot of PCs, basically, wired together with very good fast connections. Also, you use a lot of game chips, it turns out. Game chips are really cheap and really fast. So we owe a lot to the computer game industry. And all this is sorting out what those pictures, what that data means, and trying to reconstruct from that debris what happened in the original little bangs. And I find it quite poetic. This is sort of, as I said, it's a new, to make all this work is kind of like the internet on steroids, the grid, requires that these computers not only can communicate with each other and, say, exchange text files the way you do in the internet, but they actually share programs, trade jobs. They're actually functioning essentially like one giant computer over continents. But at the end of the day, and this is quite poetic, somebody sits there, looks at the screen, and decides what, if anything, it all means.